Okay, hello everyone. Good afternoon, good evening, and good morning, everyone. I'm Carlos Torres from the Beta Technological Center at the University of Vic, and it is a pleasure to welcome you. We are very excited about the response to the call for this webinar. So, we would like to know your background and all your expectations about this seminar. The agenda for today, it was divided into main topics in soil organic carbon modeling, and the next one is biogenic carbon accounting. But before to initiate with our speakers, we will do the project approach, the vision of Novafert by my colleague Jorge Senan. So, Jorge, please, if you want to introduce us about the Novafert project, please, the floor is yours.
Thank you very much, Carlos. Well, the webinar of today will bring together 2 points, soil science and LCA. And the common point is the biogenic carbon. Biogenic carbon has been recognized as one of the key elements and strategies, its management for the mitigation of climate change. And we can remark a couple of techniques like soil carbon sequestration or carbon capture for utilization and storage. Mainly we consider that agricultural soils, maybe they are a relevant carbon sink. This is now under discussion in the academia and in politics. So just to see and evaluate what is the potential of these measures, also we need metrics, harmonized metrics, and also we find different projects that aim to evaluate the potential of the soils as a carbon sink. For the mitigation of climate change. In this sense, we can find here initiatives of United Nations like Life Cycle Initiative of Align Project. Also, Novafert aims to provide some guidelines about the carbon accounting. Novafert aims to create some procedures and guidelines for enhancing the use of alternative fertilizers, of bio-based fertilizers. Probably we could start with the definition of bio-based fertilizers. Bio-based fertilizers, probably they could be defined like fertilizer products that they come from renewable biomass resources or feedstocks, and they provide nutrients to plants, mass and algae. They can come from different waste streams or biomass streams, and they can be transformed by several different and wide technologies. We can remark, for instance, composting, stripping, precipitation, but the result is that this definition covers a wide range of product compositions, inorganic and organic bio-based fertilizers, and we can find different products like compost, ammonium sulfate, struvite. No? Here, it's remarkable that most of them, they have a great content of carbon, biogenic carbon, and is therefore it's interesting to measure what is the contribution of these bio-based fertilizers to this carbon sequestration by the soil. As I mentioned, then Novafert aims is to orientate the production and application of alternative fertilizers, creating methodological guidelines for the assessment of these bio-based fertilizers, covering from the production, the storage, the distribution, and its application. The guidelines that we are developing are within the framework of the Product Environmental Footprint Initiative, an initiative of the European Commission, and the aim is to harmonize methodologies around different sectors. In the case of BP2 of the Work Package 2 of Novafert, we are developing a common method for the bio-based fertilizer sector, what is called a PEF-wise methodology. And specifically, this is normally the content of this pathwise methodological guidelines, we can find similar or common points to LCA, like functional units in the life cycle impact assessment method. But specifically, we have to address the point 5, provide guidance regarding how to handle these carbon flows during the production life cycle and also the application.
Well, before to start with the next point in the agenda, I want to remark that this webinar is developed in the frame of the Work Package 2 of Novafert project, and it's co-organized by the Working Group on Sustainability for Nutrient Recovery of the BioRefine Cluster Europe and Novafert project, which is an Horizon Europe project founded by the European Union and a proud member of this BioRefine cluster community. So now we will develop these first two presentations about soil carbon modeling, and our first speaker is Professor Jørgen Eivind Olesen. Professor Jørgen is a professor in climate and agriculture and head of the Department of the Agroecology in Aarhus University. His research encompasses experimental and modeling studies on agricultural carbon and nitrogen cycles at local global scales, including climate change impacts on agriculture and agricultural greenhouse gases and their mitigation. Also, he has participated in numerous EU projects and actions on the effect of climate change on agriculture and on greenhouse gas emissions from agricultural activities. And finally, he also contributed as an author to the third IPCC assessment report and as a lead author for the IPCC fourth assessment report, which received the Nobel Prize in 2007. So the floor is yours, Professor Jørgen.
See the presentation again.
Yeah.
Super. Okay. The carbon cycle simplified. I'm going to concentrate on the soil here. So in the soil, we can distinguish between what we could call a fresh organic material. This is what comes directly from the plants. But in the soil, this is decomposed by microorganisms. And the microorganisms respire most of this for their own sort of benefit. And what we have that then are more sort of stabilized in the soil is what I here call degraded organic material. It's mostly actually microbial residues. Anyway, the amount of organic matter or organic carbon we have in soils is then the balance between what comes in and what is respired by those microorganisms in the soil. So eventually, it's all about modeling or accounting for that balance between addition and decomposition. Yes. So this can actually be described in very, very simple ways, just by a first order kinetic formula here, where we have that the decomposition is proportional to the amount of carbon that we already have in the soil. Of course, we can distinguish different pools, and we should distinguish different pools in the soil because not all organic matter is equally available or decomposable for the microorganisms. So we typically distinguish pools with different degradability or what you can say here, different residence times. It could also be the decomposition rate here. There's another thing to be aware of, which is what we call the humification. So how much of that input is actually converted into something that is more resilient, like what we had here, the degraded organic material. So that's typically what's called the humification. And for in many, if you look at it in a simplified way, it's probably around maybe between 10 and 20%, something like 50% of this. So that's a very, very simplified way of looking at it. And of course, you can complicate it even more. However, if we look at a thing like the C-tool model here, it distinguishes 3 different pools: the fresh organic matter, humified organic matter, and something that is very, very resistant, that only decomposes at centennial scales. In such a model, there are also other factors influencing the decomposition. In the C-tool model that we apply in Denmark, and also for national scale inventories and so on, but also has been used for inputs to LCA analysis and so on. I'll get back to that. We only consider the temperature here, but we do consider a soil effect, because the humification, so how much is stabilized of that decomposed organic matter, actually depends on the soil type, mostly the clay, amount of clay in the soil, because it's the clay and the fine material in the soil that contributes to the protection of the organic matter. Of course, such models need calibration, and we typically use data for long-term experiments, both for calibration but also for testing and so on of this. So data sets we typically have here, like here to the left, a data series that shows the organic carbon in the soil, measured maybe often not every year, maybe every 5 years and so on. And then you have it over a very long time. We then have data also, or at least some estimates of the carbon input, so we can model the changes over time in the carbon in those various pools. Of course, this requires that we also initially can set the amount of carbon in the different pools. To constrain this, we can use other types of data, and this was done in this case, the radiocarbon data, carbon-14, because we have data on specific times where the soil organic matter, or rather the input, was enriched with carbon-14. Carbon-14 in this case was derived from the atomic bombs that were detonated in the mid-1900s. There are also uncertainties here, and it's important to be aware of this. Of course, as I said, the calibration of the parameters that we have in such models comes with some uncertainty, but also the initialization of the pools that we have here. What are the initial values of this is subject to quite some uncertainty. And the other thing is, of course, inputs, in particular in the carbon inputs from the crop, as you can see here, the roots and the above ground matter and so on, also contributes to inputs. And that, in many cases, is actually probably the larger source of uncertainty, and something that would also be a source of uncertainty when you make LCA analysis. However, if we look at the parameters, one way of considering uncertainty in parameters is to try to model bare fallow soils, because here we have no input. So input, carbon input with crop residues and so is not an issue. So it's mostly down to the initialization of the pools and the parameters here. So this was a comparison of 26 different models, and you can see here they are actually quite different. If you do the model ensemble, where you just take the average or the median of it, it generally responds quite well. They also tested the various aspects of it, comparing actually, do you calibrate it specifically for the site that you have, or do you use the generic version of the model? In many cases, it actually works just as well with the generic version, although there is a need at least to initialize the pools. There are other types of uncertainties related to this, and this is another study related to this, because often to derive the amount of inputs from crops, typically what we have is harvested yield. But the harvested yield doesn't give us the information on how much carbon is added in above ground residues or below ground residues with roots or exudates and whatever. That needs to be calculated from the observed yields. But there are many ways of doing this, and different models have their own procedures for doing so. So if you look at the graph to the left here, you'd see a typical input from plant residues using 5 different allometric equations. We use those allometric equations to calculate this, and it differs quite a lot, you can see, depending on which source you use for this. And if we then apply that to a particular experiment, so this is a Swiss experiment, a Swiss long-term experiment, one with no fertilization, with biological organic and with conventional farmyard manure thing, you'd see that when we apply those different allometric functions to those different to those experiments, we also get quite large differences in the amount of carbon input. And then when we applied it with the modeling, we then get quite different results, and the measured one is the one to the right. So there's actually only one of those here, the one that gives the lowest carbon input, that is closer to the measured one. Whether that actually is correct or not is still up to the jury, I would say. It just illustrates there's quite a lot of uncertainty with different procedures for estimating carbon input. There are other issues here. This is another study, again, looking at the input side of things. And here we had a standard allometric equation for deriving below ground carbon input, which is a particularly difficult thing because we have very few measurements of this across different management and so on, in particular with fertilization. So in this case, we had a standard allometric where actually the amount of above ground input is proportional to the above ground. And we had a modified one where we assumed the above ground input was fixed, constant across different fertilization schemes, which from my perspective and also some of the data we had is probably more correct. And in this case, we also were able to simulate it better with the modified one. But typically, if you would go for standard procedures, we have that other perspective on it. So we do have models. We do have quite a lot of variation between models and also how they're structured, but also quite large differences in terms of how we derive the inputs for such models. But we also want to use them, of course. And one way of using them is also to use them in life cycle assessments. And this is a paper from Peterson from some years back. If you're more interested, I can provide you with the exact reference, or you can just Google that title up there. That should lead you to the paper, because that looked at how to actually include the carbon, soil carbon modeling in the life cycle assessment, similar to the way we do with methane or nitrous oxide and some of the other greenhouse gases we typically have, because they are considered on 100 years time perspective. They're also considered with respect to what the actual CO2 emissions are. And that is not in itself a simplified thing, because CO2 that we emit, for instance, from fossil fuels do not stay in the atmosphere. That also degrades over time. So this paper gives some arguments on how actually to align this. I won't go into the detail, just say this is an issue on itself if you want to include this in the life cycle assessment studies. Yeah, reflections. There are many models here. They depend on carbon inputs and model parameterizations. There are uncertainties you need to be aware of. There's also a time scale of consideration of this, and it's not linear over time either. And you need, if you want to include in life cycle assessments, also to consider the balance with the duration of CO2 in the atmosphere. Thank you very much for your attention. I'll stop sharing. And apologies for the initial confusion. So I'll see if I can get out of this. I'll stop sharing. Yep.
Thank you very much, Jürgen. So we continue with the presentations, and then at the end of the Daniele and Professor Panagos presentation, we will have Q and answer session. So our next speaker, I suppose that Daniel present, but Professor Panagos is here too. So this presentation it's will be doing by Daniele de Rosa, and Daniele de Rosa currently has a position of a senior research fellow at the University of Basilicata. He conducts research activities in the field of environmental, soil and agricultural science, and he puts a primary goal of improving the sustainability of agricultural practices and to preserve the soil health. And his expertise it's on the integration of modeling approaches to gain insights into the spatio-temporal changes affecting the dynamics of the nitrogen and carbon cycles. So in a very recent publication, Daniele and Professor Panagos abords these measures about the different stocks of carbon stocks in Europe. So Professor Panos Panagos is he leads the development of advanced soil erosion models and contributes to the European Soil Data Center and the European Observatory of Soil. He made significant contributions to the field of soil science, particularly in soil erosion, land degradation, and soil mapping. And he has been actively involved in various internal projects aimed at assessing and monitoring soil health, promoting the sustainable land management practices, and addressing the global challenges. Professor Panagos is also involved in teaching and advocating for policies that prioritize soil conservation and sustainable land use. So please, Daniele, the floor is yours. Yeah.
Can you see the full screen or the presentation one?
The presentation one.
The presentation one, yes.
Oh, damn it. Okay. I'll try to. Okay, I have to go this way. Anyway, sorry about that. Now the full screen, I guess, right? So, hello everyone. Thank you very much for inviting me to present.
Oh, Daniele,
Sorry, Daniele.
We see the screen, our faces.
Yeah.
Please share the presentation.
All right. Damn it. Sorry. What about now?
No.
No, it's the same. If you want, I can share my screen with your presentation. Yes. So yes. Yeah, don't worry.
For some reason, the screen one doesn't recognize screen two when I go in presentation. Yeah.
Give me a second, please.
Yeah. Thank you. That's weird.
Well, I think everybody is seeing my presentation, my screen, sorry. Yeah.
Actually, I managed. If you want, I can go ahead. But well, anyway, let's go with this.
Okay.
So thank you again for inviting me to present this work. So my presentation is going to be a bit slightly different than the previous one. I'm going to present an actual modeling work that I did during my stay at the JRC. Next one, please. So just to echo the words said before by Professor Olsen, so carbon is not just carbon itself, it's linked to other soil nutrients. I mean, here for, let's say, just to make things a bit easier, I just presented the three most famous macronutrients, but you know, the whole organic matter system, the organic matter in the soil is therefore all dynamic, and all these elements are linked. But the main question is that soil carbon storage, and therefore like soil carbon sequestration that we hear nowadays, is just reducing CO2. I would say not really, because increasing soil carbon has a domino effect in one way or the other. So increasing soil organic carbon increases soil structure stability, increases nutrients and water retention, and therefore increases the resilience of the production systems. And this goes also to the other way. So if we decrease soil organic carbon, or soil organic carbon, and therefore that is linked to soil organic matter, we will have a degradation of all of these elements. Next one. So therefore, the spatial identification, especially nowadays with the importance of the soil organic, of the carbon farming initiatives, but also in the use of these advanced fertilizer that could increase soil organic carbon, it is extremely important to identify the main drivers of stock depletion, especially when you need to prepare policies at a large scale. Therefore, estimating where and by how much we are losing carbon, so where we have an hotspot of carbon losses, and by how much. Therefore, to also to include this information in a LCA study, it is a paramount importance. Next one. So I guess that most of you are already familiar with the Lucas soil dataset. So Lucas is the largest and I believe the largest in the world harmonized soil information across the globe. It encompasses around 22,000 soil samples per each Lucas campaign. It has been done already in 2009, 2015, and 2018. Actually, another one is in progress. I mean, like the 2022, the soil are being collected. In this case, we have 40,000 soil samples, and they are actually in the process to be analyzed for main soil characteristics, so soil carbon, nitrogen, phosphorus, clay content, and so forth. So the major information that you need indeed to model to model soil organic carbon in this case in space. But Lucas, like any other large soil survey, has some limitation. So until 2022, only the topsoil layer was collected. and by topsoil layer here, I mean 0.20 centimeter depth. In the latest one, the depth was increased to 30 centimeter to align with the other information, for instance, the FAO. Previously, in the 2018, we had not systematic soil bulk density, however, was updated for the 2022, but paramount importance, which was also highlighted in the previous presentation, that for each point, especially if it was not a revisited point, we have limited information regarding the management. And by the management, also need, for instance, it will be extremely important to know the history of crop residues in each particular point. Next one. So my approach was mainly a data-driven approach. So I took advantage of the repeated location between Lucas 2009, 2015, and 2018, and we directly modeled, in this case, a data-driven approach by using a statistical model, a generalized a quantile generalized additive model. So we directly model the delta, so the changes that occurred between 2018 and 2009. So we opted to model directly the delta as a static variable in this case, because if we had modeled first, for instance, the 2009, so the spatial extent of 2009, and then the spatial extent of the 2018, and then to calculate the delta by doing the simple the difference between the two maps, we could have the error that it could have been larger than the actual change, because the time frame in this case is 9 years, so we do not expect big changes. And if my spatial model has an error, when we model at this scale, at European scale, if you have an error of 10%, which is fantastic considering, the large extent, but my actual change is less than 2%. So obviously you will have your model error will be larger than the actual change. Therefore, that's why we directly model the delta SOC. We use a set of generalistic variables because, again, we have a limited information, and therefore we opted to go on a simplistic way rather than providing an over-parameterization that, of course, he has an uncertainty associated with it. So following the validation on the point Lucas, then we use the gridded predictors to upscale our delta SOC. Next one. So how much we have lost in the past decade, and by past decade I mean between 2009 till 2018. So we estimated a loss of 0.75%, which does not seem too much, but if we indeed we convert this in CO2 equivalent, we are talking about 28 million tons of CO2 equivalent per year, which is quite substantial. So the main losses, as you can see here, were mainly concentrated at large on the north and South Europe, while in the Center Europe losses were not quite important as much as indeed they would be at the two extreme of Europe in this case. Next one. So this modeling approach also provided us the opportunity to assess the model behavior, because especially when using a data-driven approach, and for instance using many variables, so one behavior could be masked, and therefore we used this simplistic approach also indeed to capture the influence of each variable, and also to compare this influence with the relevant data obtained from literature. So we use the land use as a categorical variable in this case, for predicting the land use change. So here there's nothing new, which is indeed a good news, which means that the model is not providing the right answer for the wrong reason, and therefore so we can check the model behavior. So continuous cropland, as you can see here, provided a negative influence on the delta SOC. So indeed we have a continuous losses or marginal losses anyway, while continuous grasslands provided the largest positive delta SOC. And the transition from cropland to grassland also provide a positive effect. So then with this, we could more or less quantify the partial effects of land use change. Next one. Here, another indeed verification of the model behavior. So the influence between initial soil organic carbon against the soil clay content. So increasing the initial soil organic carbon at low clay content provided a negative delta SOC. Again, nothing new, because the clay protects with the clay particles, so protects the carbon. But also, if you have a lot of carbon, you are more likely to lose carbon. While if you don't have carbon, so you, I would say you don't have much to lose. So then temperature and rainfall follow again normal. What is already known in the literature. So at high temperature and low and a low rainfall, not exactly for the same reason, but we have a negative delta SOC. Next one. So following the estimation of our losses, so then we came up with the question, because indeed we used, how can we use this information to plan for a strategic approach to increase soil organic carbon? So where is more convenient, for instance, to apply particular measures that aim at increasing soil organic carbon? Or in our case that we use as the variable of land use. So how much do I need to convert to get to increase or to reach SOC neutrality? And by SOC neutrality, I mean losses are equal to gains. So which is the best trade-off? So how much do I need to convert, where and where is more convenient to convert to achieve net zero? Next one. So here we present two very utopic scenarios. So first of all, on the top, we have the total conversion of grassland to cropland. So if we convert in a 9-year periods, in a 9-year period, if we convert 47 million hectares, we could reach a negative losses up to minus 4.8%. Vice versa, if we convert 116 million hectares of cropland into grassland, we could reach plus 12.1% in a 9-year period. Of course, those scenarios are extremely utopic. So it is unreasonable to think that to reach climate neutrality, for instance, one of the tools of the carbon, we will need to convert all the cropland in grassland, because we need to maintain food targets. But the best trade-off in this case is that if we convert 7% within each European member state plus UK of cropland in grassland, we could equal losses to gains, and therefore we could reach delta SOC 0. Next one. But of course, all this approach is indeed affected by large uncertainty. So we use a generic set of predictors. So we do not have any activity data. So we had to infer by our generalistic land use of cropland, grassland, For instance, we didn't take into account if in a particular plot, region, field, the farmer is indeed applying measure, for instance, no tillage or conservative agriculture and so forth. Therefore, this is one of the very large uncertainty. But also we have also the very large uncertainty if we want to project this in time, because any data-driven approach is extremely sensitive to the dataset boundaries. And I'm not saying just on a temporal scale, but also on a spatial scale. If, for instance, the repeated points where we didn't have many repeated points in a particular a combination of soil type, land use, and climatic condition, of course, that particular estimate will be affected by large uncertainty. However, more data, if we get more data, we will increase our spatial confidence. And for instance, this kind of exercise could be used to set a baseline for carbon sequestration scheme. Next one. So indeed, with this study, we provide, let's say, a strategic approach. So it's like during a football game. So before the game, I set my strategy. However, what if the climate change? What if we have an event which we did not take into account before implementing our practice? So then we need to move beyond the boundaries of the spatial data sets of these things. Next one. So then this is still a work in progress. So we are kind of linking together the Lucas prediction, the model based on Lucas prediction, with biogeochemical models. This will indeed increase our confidence in the temporal prediction provided by the biogeochemical model, but also will increase our spatial prediction given by the Lucas dataset. Again, this is still a work in progress. There is still a lot of coding to do, but also I forget to mention to include here, we are also linking the measured soil organic carbon fraction, because also as explained in the previous presentation, the initialization of the pools, it is indeed a component. It is an important component when using these models. So therefore, in this study, we are also trying to link the measured carbon pools with the theoretical pools that these models use. Next one, and I guess I finished. So thank you very much for, and sorry for the technical problem of the screen. Thank you.
Okay. Now I think that we have time for a few questions. What do you think, Carlos?
Yes. So we have two questions in the chat. And well, I was sorry, I taking advantage of my position as moderator to develop one or a couple of questions too. But if you prefer, we can start with the questions in the chat. So Jean-Philippe asked if what do you think about the sticks model used in France by INRAE to assess the sea behavior in soil? Well, I think that is for Jorgen, but Professor Panaus and Daniele, feel free to answer if you want.
I mean, there are many of these models. Basically, they're structured around the same thing. Some pools that are interlinked and based on first order kinetics with some sort of modifying factors for this. So I don't necessarily see that any of them may be better than others. and this is to some extent also what the intermodal comparisons show. It's much more really about the parameterization, both of how you parameterize the models, but also how do you quantify the inputs, because much of the inputs that we have, we don't have good data for. We make assumptions on this. So this is what I was also trying to argue for the uncertainties.
I don't know if Daniele or Professor Panaus wants to add some. You are mute, Daniel.
Muted, Daniele, muted.
Yeah.
Muted.
Yeah, sorry. So I totally agree. There are many models, and I would say that also many of these models are originated for the same structural framework of modeling soil organic carbon. So is indeed the large uncertainty is in the model input rather than the model itself, because they have been already tested in incubation study, in the field study, and they provide all very good results. But indeed, the information, the amount of information that is required to have, let's say, confidence results, it's quite large, and we hope to reach that. But I would also highlight the fact that this data, especially for the management practice, we have this information at member state level from the GSAA data, which some country already made publicly available, some other countries not. But in the future, we hope that to have this information from every member state.
So if I could add maybe something that we've been looking into, and where I think we have maybe even greater uncertainties, because Danielle, you also said, okay, converting through grassland would enhance. I agree. However, when we look at different grasslands, there are really so many different types of grasslands, some more intensive, some more extensive, and we have relatively little information on what that means for carbon inputs and also stabilization and so forth.
Yeah. I mean, absolutely. Also, the time frame of some experiment, especially when the conversion from cropland to grassland, to see some considerable effect, you're gonna need 20 years. So that's what for this long-term experiment will be quite handy on this.
Well, I think yes, yes, Jasmine did another question, and how would you link your research with LCI modeling regarding land use and land use change? I think this issue are well, there are a lot of information about it in papers, but maybe if we can combine this question with the measure of the uncertainty, because I think this is a very big question, because this and try to put in the context that they are developing a lot of systems or models for monitoring, reporting, and verificate these soil carbon stocks for develop maybe carbon farming or to put carbon credits in the market. So,
yeah, but so I think that the way, I mean, we have some challenges, I would say, with the accounting of these, because when we talk about carbon in soils and in vegetation and so on, that accounting is under the LULUCF sector, which addresses the amount of carbon in the various systems, right? Whereas when we, so that's fine. It's all about the carbon accounting, stock-wise. When we otherwise talk about or try to quantify the climate effects, the CO2, whatever, equivalent effect of things, we tend then to think that a kilogram or gram of carbon that we have in soil can be directly converted to a similar amount of CO2 in the atmosphere. That is not the case. Because when we talk about the CO2 in the atmosphere and emissions and so on, that is where we have, that is affected by also sinks and so on of that CO2. So converting it to an equivalent CO2 effect, we actually tend often to ignore also in our LCA assessments. It's really more tricky than just trying to convert a gram of C sequestered into a similar amount of CO2 and then assume that that has equivalent effects in the atmosphere. I'm afraid we don't have too much time to go into detail. I'll just put that as a caveat.
Yeah, well, we know we want to your presentation for 1 or 2 hours, but it's not possible today. But thank you very much, Daniele, Professor Panagos, and Professor Jorgen. So if we are not in time, but we need to go to the next session. That is the session about the LCA framework. So, Jorge, please, over to you.
Well, thank you very much to the previous speakers. It was a pleasure to see the ideas about the soil organic carbon. Now it's time probably to go to the LCA developers and practitioners, to LCA methodologies. And we have 2 fantastic panelists and speakers. I would like to present the first one, that is Professor Massimo Poisol from the Department of Planning of Aalborg University. He's teaching and researching about different fields like sustainability, industrial ecology, life cycle assessment. At Aalborg University, he's member within the Danish Center for Environmental Assessment and Tech Center for Circular Economy. And the main focus of his research is emerging technologies, in particular technologies that are in the transition towards a circular, blue and greener bioeconomy. He's investigating about using interdisciplinary methods and quite oriented to stochasticity and stochastic life cycle models. Also putting explicit attention on uncertainty and scenario analysis. Probably most of the sectors that he's addressing are bio-based sectors, and in particular in a Light New project, he's coordinating this project and that it aims to harmonize methods of life cycle assessment of bio-based products. Therefore, he will have a great speech in a great, he will bring us some of the greatest ideas and the state-of-the-art trends in LCA about how to account this biogenic carbon and how it's the relation with the biomass feedstocks. Thank you very much, Massimo, for your presentation today, and the floor is yours.
Can you hear me first?
Yes.
Yeah, good. And I hope you can see the presentation here. Well, from the start, maybe. Wait a second. Here we go. So I hope you can see the screen. Well, thank you, Jorge, for your very good introduction, and I hope to live up to the expectation. So I was
apologize, Massimo, we cannot see your screen.
You cannot see the screen?
Yeah, we saw before.
So you saw it here?
No, we cannot.
Wait a second. I'll try again. Where are we now?
We saw it for a few seconds.
Yes, I'll try again.
Okay.
So now you see it, and now you see it?
Yes.
Yes.
Oh, that's very good. Okay. So I was asked to make an introduction to biogenic carbon accounting in an LCA framework. And without knowing exactly the type of audience, but expecting that it was a bit mixed, and I think it is. When I made this as a very general introduction, and maybe for some of you things will be too simple, for some of you will be new, but I hope there is a little bit of useful information for everybody. And I should mention that this work was, and the time for making this presentation was taken from the Align project that I'm coordinating together with colleagues here at Ruhr University, and in particular from the work package 1 on shared modeling framework and learnings. Yes, so as we discussed before, also in the previous presentation, we have as a problem that we have to inventory properly the carbon flows in LCA, and in particular when it comes to bio-based products, these have different lifetime and different end of lives. So what happens after the bio-based product is used is different depending on the product. This means that we have carbon uptake and release at different points in time. So when I grow some biomass to have a feedstock to produce a bio-based product, I have an uptake of carbon in the biomass, and then the product is used and this has this carbon in stock in a way, and when the product is reaches its end of life in a life cycle perspective, and then the carbon might be released at this point. So we have this difference in this happens at different points in time, but in LCA time is flat because emissions at different points are counted as they occur in the same moment, in fact. However, we know that the impact in terms of global warming, in terms of relative forcing of the carbon uptake and release depends very much on the timing, and this is shown by previous research that argues that a dynamic LCA approach is the best way for a consistent assessment of the impact through time of all the greenhouse gas emissions and sequestration, positive and negative. And this has been published a long time ago, and we all agree on that. And that's the proper way of doing it. So the question is, what, in order to make a better or more scientifically sound approach or assessment of the bio-based products, we need to understand what are the dynamics of carbon uptake and emission in these type of products. And then how can we make an LCA inventory that considers these dynamics accurately? And then the question that we try to investigate in our project, for example, is whether this type of LCA model, which is a bit more complex, will improve the assessment of the bio-based products. So let's look a bit pragmatically and also critically to this, what I just mentioned. So when is a dynamic approach relevant? Not always, in my opinion. So we have, it is very relevant if we have feedstock with long rotation, for example, in a forest, where you can have rotation times up to under 50 years. So trees that are grown for under 50 years, with very slow carbon uptake and different profiles of carbon uptake. And then a time differentiation becomes relevant, I will argue. Then in the case of long-lived products, for example, wood and other construction materials that can be used, also insulation material and other bio-based products that can be used in construction, for example, and are like incorporated in a building for a long time, or reused in several life cycles so that they stay in the technosphere for a long time. And you can see some publications here for some example of this type of products. I would argue it is less relevant instead for short-lived products from short rotation feedstock. And I have here an example of a plant-based bioplastic intended for food packaging. So if you have plants that grow during one single year, and then you produce a packaging material, a bio-based packaging material out of that, it is used in a couple of months and then is sent to an incinerator and burned. Then we have carbon uptaking and released quickly, and although a dynamic model is still formally the most accurate choice, practically I would argue it's overkill. So from a pragmatic perspective, if you're a practitioner, I'm not sure you are. I mean, I'm not sure you get something out of so much better results or different or better interpretation by increasing the complexity of a model to this extent. And then we have a case of short or long rotation feedstock where we have long-term carbon storage in soil, which is a bit the topic of this seminar today. So in this context, I think it might be quite relevant. Then we have the issue of accounting for biogenic CO2, and here I would like to acknowledge our partner in the Align project, Laurie Hamelin from Toulouse, who has prepared initially the slides, and I've taken this from her, so she should have all the credit. So there are different approaches for accounting for biogenic CO2 in LCA. One of them is called the 0-0 approach. So this means that the absorbed and released carbon dioxide and other greenhouse gases, carbon dioxide, sorry, are accounted with a characterization factor of 0 in the global warming metric. Whereas the induced sequestration has a characterization factor of 1 and a negative flow. What does it mean? It means, as you can see in the figure here, that if I have biomass growth, then I invent there is some carbon taken, but this environmental exchange is then multiplied by a characterization factor of 0, so it doesn't count in your impact assessment. And the same for the release. Instead, if there is a sequestration, this means a very long-term storage. This is accounted and as a negative inventory, negative flow, and multiplied by a characterization factor of 1, so that it will count as a negative emission effect sequestration. What are the potential issues with this approach without entering any pro and contra? But one of the potential issues is that it can give a false impression that there are no climate effects from the use of biomass. Important carbon flows are made invisible in a way from the assessment. Mass balances can be distorted when carbon is emitted back as different type of greenhouse gases, and the temporary storage between the uptake and the re-emission is not reflected in this approach. Yes, then there is another approach is the -1 + 1. Now this means that the uptake from the atmosphere is accounted with a characterization factor of -1 and the release with a characterization factor of +1. And all the different flavors of this in a way. So if your exchange is called biogenic and is counted with a negative, when you change the characterization factor to reflect this, but the substance is that both of these flows are accounted, and only net flows are accounted, and sequestration is not assigned a flow. So you can see it in the picture. I have the uptake and the release, and I don't have the stock. So it's all about the flows. What are potential issues with this approach? Instead, you might have, maybe misleading in a strong word, but let's say misleading results when the system boundary is cradle to gates, because you end in a situation where you have carbon negative products. So if I have a production of bio-based product, for example, from a certain type of biomass, there is a carbon uptake and there is the use of a product, and that's it. And then, of course, I will only account for the negative flows, and then my product will be carbon negative. But we all know that the product will also have an end of life, and therefore something will happen to this carbon again. It will be released at some point. So by having a truncated or partial system boundary, this can give a wrong impression, especially when producers of bio-based products market or do marketing in this way, like, oh, we have a negative carbon negative product. Another potential issue is the how to account for this absorption, in fact. So a common assumption is to account for the carbon that has been uptaken by the crop, for example, or tree, equal to the carbon in the product, which is a sort of underestimation sometimes, because it doesn't account for the carbon in crop residues below ground and conversion losses. And this error can be problematic, especially if something happens to this carbon, for example, in the soil, is converted into some other type of greenhouse gas, for example. Or a better approach could be, another approach could be, sorry, I can't see my slide here, basing this on the net productivity or the crop yield, which is a more rigorous approach. And you can find some literature about this here below. So it is, the challenge is basically how to properly account for this, because there are uncertainties as well as we have seen in the previous presentations. Okay, how much are these two approaches used? According to this publication here, what we retrieved, most industrial guidelines seems to prefer the +1 -1 approach. I mean, it's very difficult to make a trend, but that's what we can kind of conclude at the moment. And the 0,0 used in the PEF, PF, CR category rules. Although I was looking at the PEF today, it's a bit more nuanced than this actually. But yeah, that's more or less how we are with that. Yes, next slide. So we also have been looking into the EN 1670-60 2015 standard for bio-based products, in particular the LCA part. And this here I have to credit my colleagues Agneta Goes and Kira Langs, who have been doing this analysis. So this is a common standard for terminology, bio-based content determination, LCA, sustainability aspects, and declaration tools of bio-based products, all of these. And the LCA part is very much based on the ISO 1440-44 series. And this series of standards, in fact, focuses on the products that are, excludes the products that are related to food, feed, and energy. It says all the others. So they also define fossil and biogenic carbon flows. A biogenic carbon flow is a carbon derived from biomass, and that's it. And the recommendation is that, or the guidance is that both fossil and biogenic carbon need to be accounted for, although they should be included and listed separately in the inventory. So they have to be accounted and also made separate. In the standard, they mainly suggest to use, they accept both methods, but they present first with -1 +1, which is exactly as I explained before. So -1 is for atmospheric carbon fixation during growth, and +1 for carbon emitted and permanently sequestered as a characterization factor. Yes. But they also accept the 0,0 approach. And then, because the previous recommendation was to inventor all, to count all the flows, but then the characterization factor is 0. So they are multiplied, but you account them, but then they disappear in a way. And then they also recommend a sort of temporal differentiation according to the AICD method that basically discounts, let's say, or reduces the effect of a specific emission if this is generated later in time, using this equation and up to 100 years. So you have all the mass of the greenhouse gas emitted is multiplied by the time of emission and the global warming potential, and then divided by 100. So everything over 100 disappears, and the later it is emitted, the lower the impact, which is I haven't never seen it applied in practice, to be honest. there's also a bit of a simpler method that what is proposed in the papers that I presented in my first slide, because we know that the global warming potential is a non-linear function. So this is a linear function, and it's not very clear to me why it is used in this way and whether it's formally correct or not. Here an example also from the standard that I wanted to show you. So here is just an example of how the calculations are to be done. And what is interesting for me to show is this about the cradle to gate type. I don't think they chose a super fitting example in this case, but you can clearly see that we have a comparison between a fossil-based product here on the left and a bio-based product on the right. And then you see in gray here, the bio-based product has some carbon uptake in the production stage or upstream, let's say. The terminology is not super clear. And then this counts towards the total emissions negatively, so reduces the total emission of a product, and then decreases the overall impact of the product, of course, on a cradle to gate boundary. Now, what is if you imagine that this 22 is not there because there are no other emissions hypothetically, or they are very little, then you will get a carbon negative product on a cradle to gate basis, which might be, when communicated in the wrong way, can be very misleading, because this is not a carbon negative product when you don't account for the end of life. So this again to making a point before. Coming to a conclusion, we don't have a final recommendation yet from our project because it's still ongoing, and so I'm not going to present that. So this is not, please don't take this as a result of our project yet. But what we discuss usually, what we are discussing is some type of what is the most sound way of doing this scientifically, and we are of opinion currently that is good to account for all the carbon flows, either absorbed or emitted as they are, because this is the closest way to model the reality. So we always have a principle that we try to model as close as possible to reality. And then to make some conservative choices on the releases for cradle to gate studies to avoid the carbon negative products and misinterpretations that can come from this. So we are definitely not recommending at the moment to use the -1,0 approach, or to use the -1+1 approach so there has to be a sort of interaction between the choice of approach and the type of study and the system boundary. If it is a cradle to gate, this clearly doesn't work for us. So we account for carbon dioxide, the carbon biogenic or fossil or both, and to stay on the safe side and to be complete, we recommend at the moment, or we think that it's best to include at least one indicator that integrates both type of carbon. And yes, that was all from me. You can read about the project, more about the project on this on our website, and also join our newsletter and stakeholder network to get informed about the results. And again, I would like to thank the collaborators in the project for that, also contributed to this presentation, and also thank you for the attention today.
Thank you very much, Massimo, for your presentation. I think that it was super complete in terms of what is the current practice and trends of carbon modeling in LCA. And also, we can move towards the next speaker with all these basics and towards more orientated presentation about shock modeling and LCA that we expect to join both walls, or to try to finalize and conclude better. Of course, we are having a great debate in the chat, so we will answer these questions later at the end of the Crystal presentation. Crystal, are you here?
Hi.
Okay. Okay. So I'm pleasure to here to present Cristel Andrade Diaz from the University of Toulouse and Universidad Técnica de Manabi. She's currently an associate professor in the Technical University of Manabi in the Chemical Process Department. She has been working for 5 years teaching in chemical schools of engineering, and she has been a postdoc in University of Toulouse. Also, she has a background in the private sector with ISO certifications and agrochemical studies in the industry. Probably we should highlight her research in the use of crop residues in the supply of renewable carbon in the bioeconomy transition, so towards the bioeconomy transitions and low fossil carbon economies. She's mainly focused on carbon sequestration, negative emissions technologies. I guess that she's using -1+1. Let's see what she's explaining. And her latest research works involve this coupling of soil modeling tools and LCA studies to provide an overall vision of the possible technologies towards net zero goals. So thank you very much, Cristel, to be here, and the floor is yours.
Let me see how to share. Is it sharing? My presentation is sharing?
Yes, Cristel.
Okay, then thank you for inviting me today. I'm going to present more of a case of study that couples what we have seen over this webinar. So I will couple a soil organic carbon modeling where we included the biofertilizers into a LCA framework for the specific case of crop residues. Crop residues are key to supply renewable carbon because they are abundant, flexible to supply several pathways, and they pose no land or food competition. However, they are a source to maintain the soil organic carbon stocks balance, and therefore their harvest is often limited to 15 to 60% of their theoretical potential. This creates a trade-off between harvesting these crop residues to supply carbon to the bioeconomy or leaving them on the fields to maintain the stocks. So in our study, we wanted to know if it was better or if it was possible to harvest the crop residues to supply renewable carbon to the bioeconomy while maintaining the stocks, and if there existed any trade-off between the stock sequestration potential and the full environmental impacts of the bioeconomy strategies. So what we did was perform a SOC modeling with a model adapted for recalcitrant bioeconomic co-products, which are considered today biofertilizers, with an LCA framework for the full supply chain of the selected pathways. So this study was done in several steps that are detailed in the publications, but today I will focus more on the results. So basically the framework contains a SOC modeling stage, and with the SOC model results, we use them for the consequential LCA. So in the soil modeling stage, we define a carbon neutral harvesting rate, which is the maximum amount of crop residues that can be supplied to the bioeconomy if the recalcitrant products are returned to soils as biofertilizers. We did this for 4 scenarios where we consider the return of the biofertilizers, which are recalcitrant carbon. So for pyrolysis, we consider pyrochar, gasification gas char, hydrothermal liquefaction with hydrochar, and anaerobic digestion with digestate. It needs to be highlighted that the study is relative, so we compared what we observed in the bioeconomy scenario versus a reference one where the business as usual is to leave the crop residues not harvested. As soil modeling is spatial and temporal explicit, we defined a temporal scope of 20, 50, and 100 years, and the geographical scopes was defined for a temperate context represented by France and a tropical one represented by Ecuador. So the baseline was created for France by INRA with the 4 per thousand project, while for the case of Ecuador, we created in this study. And the soil model used was AMG for France and RODC for Ecuador. Both of them were adapted to include the recalcitrant characteristics of the biofertilizers. The cropping systems in France yielded over 60,000 simulation units, while in Ecuador it was over 15,000. So the results in the French case at the end of the simulations are now shown. First, 10% of the area of France does already use the crop residues, so those are not available for the bioeconomy, but all the rest of areas could export all the harvestable crop residues with not only not stock loss, but with expected stock gainings in all the areas. It was seen the same for the gas char scenario, although the amount of stock sequestration is a bit less in this second case. For hydrochar, as this is less recalcitrant than pyro and gas char, we observed slight stock losses at the north of France, and it gave a potential of 88% of the area that could export all the harvestable crop residues, while in the case of digestate, it was defined as 50%. So these percentages allowed us to observe an extra potential of 71 to 225 petajoules that can be supplied for the bioeconomy in France without decreasing the stocks, but mostly increasing it in all the areas. So in Ecuador, we observed similar results with the pyrochar and gas char being able to allow us to harvest all the harvestable crop residues with no stock loss, while in the case of hydrochar and digestate, we observed stock losses in all the simulations. So these two were deemed as not interesting for carbon sequestration in this tropical context. So the results were an extra 113 petajoules for the bioeconomy in Ecuador. Once we had the sub-modeling results, we applied it for LCA on a relevant case. Here we show the maritime biofuels because this is one sector with one of the biggest emissions worldwide, and sustainable maritime fuels are considered an alternative towards the emission reduction goals. So in this case, what we considered was that the crop residues were used to produce the sustainable maritime fuels, and the co-products were returned to soils as biofertilizers. And we did it for two extreme cases selected from the soil model case, which were pyrolysis and anaerobic digestion. And we did it for the scope of France, considering a future optimal performance. We selected France because of the availability on data. So the consequential LCA had the goal to reveal if there existed any trade-off between the carbon neutral harvest potential and the overall environmental impacts of the full supply chain to identify the best management option of these crop residues. So the functional unit was the management of 1 wet ton of harvestable crop residues per year, and we performed a well-to-wake life cycle assessment for 5 impact factors, which were climate change, respiratory inorganics, freshwater eutrophication, marine water eutrophication, and water use. We selected those because they are deemed key in bioenergy production. And we use the environmental footprint approach, considering that the biogenic carbon was using a 0-0 approach, as just presented before by Massimo. So the system boundaries in our study presented 3 scenarios. One where the crop residues were left on the fields. A second one where the crop residues were used to produce hydrotreated pyrolysis oil, here HPO, which was used to supply cargo ships, avoiding the use of heavy fuel oil. And a third scenario where we use them to produce liquefied biomethane that avoid the use of liquefied natural gas in cargo ships. So in the second case, the biochar was returned to soils as a carbon sequestration strategy. And in the third scenario, the digestate was used as a biofertilizer, avoiding the use of mineral fertilizer. And the CO2 was recovered to avoid the use of liquid CO2 production. So the results are now shown here. I need to clarify that for the business as usual, we show the biogenic carbon only for illustrative purposes. This will represent the zero impact, and this is the net impact of the scenario. And for the management of the recalcitrant coproduct, we observe opposite trends between the technologies. So for the HPO, we observe that actually the biochar is a big contributor for the avoided emissions and climate change, while for bio-LNG it has positive emissions. However, as an overall, bio-LNG has a better environmental performance in the climate change impact, mostly because of the upgrading process that allows recovery in the CO2 and also the avoided fossil fuel. If we look at all the impacts altogether, we see that the digestate has the same trend among them, constituting positive emissions in all the impact categories for bio-LNG, while in the case of HPO, it is interesting only when we consider climate change. Then another point of interest among the results was that upgrading the biogas using a cryogenic technology that allowed to recover CO2 allowed to have savings in impacts as freshwater eutrophication, climate change, and water scarcity, while in the case of HPO, the upgrading technology selected actually caused positive emissions. And also, it is interesting seeing that the use of these co-products to avoid the use of agrochemicals actually produce negative emissions, which help in the environmental performance of the technologies. So after we have these results, we scaled it up for the results obtained in the sub-model to couple both the results. So in the SOC simulations, we observed that with pyrolysis, we could sequestrate 7,740 kilotons of carbon, while for the case of anaerobic digestion, it was only of 7.6 kilotons of carbon. And this represented a C-neutral potential of 18.7 megatons of dry matter for pyrolysis, but it was only 10 for anaerobic digestion. So when we scale the results from 1 ton of crop residue to the whole carbon neutral harvesting rate, considering the SOC stocks, we observed that there is a change in which was the better technology. So for 1 ton, it was anaerobic digestion, but if we consider the SOC sequestration and the carbon neutral potential, it becomes the pyrolysis. However, for the eutrophication freshwater, we do not see any change on the trends. And it was highlighted that for the cases of eutrophication, marine and respiratory inorganics, anaerobic digestion is actually producing positive impacts, while for water scarcity, it is also the best performing technology. So here we see that the pyrolysis case is actually negative in all the impact categories and is also the one that allows to have the highest carbon sequestration potential. However, if we focus on eutrophication, freshwater, and water scarcity, even though for carbon sequestration in anaerobic digestion is lower than pyrolysis, it produces a better performance in these two impacts. So in conclusion, with the study, we noticed that a carbon neutral harvest rate will allow to supply extra 71 to 225 petajoules and 113 petajoules for France and Ecuador. This is interesting because they represent the gross electricity generation in Greece and Austria. And this will be done without losing stocks, but actually increasing the SOC stocks compared to a situation where they will just be left on the field. If the goal is to maintain or enhance the SOC stocks, then 100% of the crop residues could be harvested for biochar or gas char, 88% for the hydrochar, and 50% for the digestate if we consider France. But if we consider the tropical context of Ecuador, hydrochar and digestate pose no carbon sequestration potential, and then the sequestration, the harvesting rate will be 0%. We observe for the LCA that the HPO and BioLNG can offset 90% of the greenhouse gases emissions of the traditional fossil maritime fuels. And that for France, we found no trade-off between the self-conservation goals that we started the study with and the environmental performance of the technologies when we couple these results with the LCA. So the study had many limitations, as it has been said during this day. The first one is a lack of data. So both the stock modelings and the LCA frameworks require heavy loads of data, and for spatial explicit studies, many countries don't have the required data sets, so many considerations need to be done in order to produce this kind of studies. Also, upscaling laboratory studies to represent real environments is still a challenge, and this is a big limitation to include the biofertilizers within the soil models, because it is more than carbon. It goes beyond carbon, and it should include other nutrients and microorganisms' response to this recalcitrant material. So these studies had many sources of uncertainty, where we should highlight the baseline data, as it was said in the presentation that was before me. The baseline data is very uncertain, then the results will thus be very uncertain. The co-products characteristics, they will vary between the conditions of the technology selected and how we integrate the co-products within the soil models. There are models that are more complex or simpler, and so it will change a bit the results. And also in the case of the LCA, the assumptions considered for the process stages are a big source of uncertainty. Moreover, there is a big need of computing power. These spatial explicit studies with many simulation units and sensitivity analysis coupled with LCAs require big space for storing the data and big computing power, because they're very time consuming. And also, as I said before, returning the recalcitrant co-products goes beyond the carbon, and they could affect the fertility of soil, the future yields, and this needs to be taken into account in the LCA studies, which is still a bit difficult to consider. So, as a take-home message, we can say that coupling the spatial explicit submodeling and LCA allows to find hotspots where these crop residues can be harvested to supply a given bioeconomy pathway, while we ensure the best environmental performance and soil carbon conservation. And then we will also highlight places where we should not remove these crop residues. Scaling the environmental impact to a national carbon neutral potential can change the results of an LCA to decide which is the optimal pathway. Despite a low stock sequestration potential, a given technology can be more attractive if all the environmental impacts are considered, as in the case of digestate, where we saw low stock sequestration potential, but it was a better performance technology for some impact categories. And defining a carbon neutral harvesting rate ensures to supply the bioeconomy while we maintain the stocks and reduce the environmental impacts, compared to just leaving the residues directly into the soils. So in the perspectives of the study, because this is a study that continues, it's going on, we need to improve the inclusion of the stock model results within the LCA. Currently, there are some average characterization factors that are being used for stock depletion that are included in LCA methodologies. So these factors can be proved based on a spatial explicit submodeling given for a spatio-temporal context, and there are many projects that are trying to gather results for this to include them in their national accounting factors. And the SOC-LCA coupled studies are very time consuming, so they should be developed in automatized tools that integrates the SOC model within the LCA framework to save some time. So thank you for your attention.
Thank you very much for both speakers and Crystal, Massimo. Thank you very much. I think that together with the previous speakers, we had a great overview about the complexity of the soil organic carbon, biogenic carbon in general. What are the difficulties in the modeling of mass balances, the temporal dimension, all of these issues related. And I'm going to introduce one question that appears before in the previous session, but I think that it was mentioned in these two LCA presentations that we have. It was with UVic-UCC. Thank you for your presentation. You talk about uncertainty in estimating soil organic carbon contents and accounting for changes with further usage in LCA. Is there a method or exemplary usage to include and differentiate this in uncertainty assessment on LCA results via propagation of uncertainty? I think that he is or she is asking about which kind of methods are in LCA to estimate or integrate the errors in the inventories characterization factors. I don't know, Massimo, probably you want to answer these questions.
I have answered some of them in the chat. Which one? I think the one was for about uncertainties for the last speaker.
Yes, which kind of methods do you think that they can be of interest for LCA practitioners to integrate uncertainty and variability in LCA?
Oh, that's a very broad question. There's a lot of methods you can use to look into the uncertainty of the LCA models. But and I don't want to enter in all of them, but what I maybe can say is that please do it because this gives a lot of added value to the model. So yes, do the uncertainty analysis. It's important. If it doesn't have to be the most complex thing in the world, but think about it. Think about the uncertainties and try to quantify them. Especially we see. I think most of the literature agrees that uncertainties related to the modeling choices are the most prominent in many studies. So perhaps even in general. So focus on your assumptions and evaluate whether they are sound, and if you change them, what happens to the results. Yeah, I mean. I could talk for hours about this. I don't want to really enter into that. But yes, please do the uncertainty analysis. It's very important.
Crystal, do you want to add something?
Yeah, as Massimo said, there are many methods. We, for instance, as we do the soil modeling first and then we include it in the LCA, it will be very time consuming to do, for instance, a very long simulations. So what we did was considering the extreme cases and did many simulations, because what we did was include the SOC result. So more uncertainties, more simulations for the SOC model, and then they are considered within the LCA. So what we did is to take on the extreme values shown in the literature, and we simulate all of them. So actually for the French case, we had 100 simulations, and for the Ecuadorian case, we had 150 simulations, and all of them were considered then in the LCA.
Okay, thank you very much. I think that there were two answers to these questions. The first of Massimo probably is more related to these methodological divergences that you can find and methodological choices, and more numerical methods there are probably but probably they are quite time-consuming. Some things like Monte Carlo and so on, where you can introduce this uncertainty, these numerical uncertainties and variability. Several questions about variability and uncertainty. Probably I appreciate, Massimo, your time now and your answers here in the chat, because I unfortunately now I don't have questions that you did not answer, but I don't know if you want to comment something about the truncated systems, or what are the relations between zero input and release modeling, -1 + 1, and the system boundaries, because in your presentation it was pretty clear that 0, 0, it has somehow it's useful at the end when you are talking about truncated systems, probably.
Yeah, I mean, the point is that we should try to avoid giving a misleading result, right? So if the choice of this 0, 0, +1, -1, or it has to is related to the choice of the system boundaries. So both methods might be okay, but it depends in some situations, but not mixing. But if you have a situation where you have a life cycle assessment study and the system boundary of your product does not include the end of life, and you know something is going to happen to this carbon in the end of life, and you exclude this from analysis so that you only show that some carbon is uptaking by some biomass growth, and then this carbon is in your product, and that's it. And then your product has a negative value of global warming. There is some sound in the background, sorry. This is misleading. Mm-hmm. That's just as it is, because we see this sometimes, marketing, they come up, oh, we have a negative bio-based product here. This is not true. I mean, I'm sorry for those people, but I do understand that especially in industry, there is a need to have studies that are cradle to gate, and that, yeah, I understand that. But be careful, because it's very easy to make misleading statements in this situation where you account only for one flow and you don't account for the end of life. I hope this is. I stressed this point several times. But I hope it's clear now. Maybe. Okay.
Well, thank you very much for your answer. Now, Carlos launched a poll just to throw the ideas about which are the main challenges in soil organic carbon accounting and its translation into LCA, introduction into LCA. We are running out of time, so feel free to write the answers now. Through the meanwhile, I don't know, Carlos, if you want to comment just one or two remarks and highlight some messages from today's webinar.
Yeah, well, I take some notes about the soil carbon modeling, and maybe Jorge can do the same with the LCA approach to highlight this kind of remarks. So in the field of the soil organic carbon accounting, well, I think one of most relevant thinking is about the carbon cycle is linking with another nutrients such as nitrogen, as Jorgen said, and maybe this is I want to add some more, and it's important to consider in certain regions these links with the soil inorganic carbon and all the stocks of the inorganic and organic carbon to take into the account for measure the environmental impacts or this approach in LCI. The second one is that there are several models for accounting soil organic carbon, but it is necessary to measure the uncertainty of these models For sure, increasing the data collection and using this kind of hybrid or hybrid approach like field sample, earth observation methods, and remote sensing, for sure, to establish a baseline to compare with different scenarios. And then I think we can a lot of data to coupling with the LCA framework.
Just probably to bring a few remarks, probably more oriented to the LCA. As we see today, there are several issues in the LCA modeling of the organic carbon. We can find issues in the methodological choices, in the inventories and in the characterization factors, indeed. The accounting of the fact, it's difficult, and the time dimension, it's a key point here. And also I would like to highlight and to bring some messages that soil scientists, the first two speakers wrote, that we are quite oriented or analysis in the carbon, but we also have other nutrient cycles that they are affected. And in most of the cases, we also are not seeing them with all the detail that we should. Probably as an LCA practitioner, we have an important path to walk before us. And let's see what we can do as a community in the next years, but our challenge is there. Okay, so here we can see the polls some polls answers. Data, it seems that is the most challenge in the SOC accounting and its introduction in the LCA. So just to finalize the webinar, probably I would like to appreciate the time of the speakers and my colleague Carlos in organizing this webinar. It was quite fruitful. I think that all of the speakers they have a really high level in its expertise and its topic and their topics. And thank you very much for all of you, and also for the participants. We arrived to 130 participants. Now we ran out of time, so we have less, but I think that it was quite successful webinar. Carlos, do you want to add something more and to conclude?
Yes, only to conclude, remember that stay alert, because we will share the link with the recording of the presentations in the Novafert and BIOREFINE clustered platforms. And on behalf of the sustainability working group and the Novafert project, we want to thank for all the interested people, and for sure for the brilliant participation of the speakers. So thank you very much, and see you in the next webinar.
Thank you very much. See you soon.
See you.